A container is a sandbox for a Linux process. It isolates processes in the container from things running outside of the container. Thus, containerized processes are unable to see or access external processes, file system mount points, network stacks, and so forth. Furthermore, a container can restrict the amount of compute resources, like CPU and memory, available to the processes in the container. Note that containers don't restrict resources by default like a virtual machine would, but they can be configured to do so.
Linux containers are a feature provided by the Linux kernel. They've been around for quite a few years now, but they've never been particularly user-friendly, and so they weren't widely adopted. But then at PyCon 2013, Solomon Hykes introduced Docker. Docker is an open source program which greatly simplifies the process of creating and running Linux containers. Users interact with Docker via a command line interface, which is nice and user-friendly. Meanwhile, under the hood, Docker deals with the nitty-gritty details of working with the Linux kernel to create and run containers. But that's not all that Docker brought to the table. It also introduced a standard package format for applications called a Docker container image. A Docker image packages together an application along with all of its dependencies, such as config files, DLLs, jars, environment variables, even the OS file system that it runs on. So, what's the purpose of a Docker image? The answer is that an image is a template for new containers. Thus, Docker can take an image and use it to create one or more Linux containers. Every container created from an image is unique, and yet they're all clones of their parent image, and each holds the containerized application plus all of its dependencies. To use an analogy from object-oriented programming, a Docker image is kind of like a class, while a container is kind of like an object. Now you have a basic idea of what Docker, the open source software program, is. Note that Docker is also the name of the company which originally created the Docker software. Docker Inc. makes its money by hosting private image repos and containerized applications in the cloud. Docker is made up of three key components. The first two components are the client and server. The server is a daemon process that runs in the background waiting for orders from the client. It's what does all of the heavy lifting of building images and running containers. The Docker client is the second component. It provides users with a command line interface for controlling the server. The client and server communicate via RESTful web services. The third key component is an image registry. The purpose of an image registry is to act as a repository for Docker images. You can then pull the images down to your computer, where the Docker server will use them to create and run containers. The most well-known image registry is Docker Hub. It's the official public registry run by Docker Inc. It contains tons of images which were created by the community and are free for anyone to use. In fact, Docker Hub is the default image registry when you install Docker. But there are other container registries, such as Key and Google Container Registry. But you don't have to store your images in a public registry. If you're working on something proprietary, you can store your images in a private registry. Companies like Docker and Google will host a private registry for you for a fee. Alternatively, you can run a private registry on your local network. That covers the Docker architecture.
So far, I've given you a brief glimpse of what Docker containers can do. But if you want to understand all of Docker's benefits, it's helpful to learn how containers and images work under the hood. Furthermore, knowing these low-level details will give you the background necessary to design your containers so that they're small and resource efficient. Therefore, let's spend a few minutes going over how containers and images work.
You might think that under the hood, a container is some sort of file or object. It's not. There's really no one thing on your computer that you can point to and say, that's a container. Conceptually, a container is just a sandboxed Linux process. In reality, a container requires multiple different Linux kernel features to isolate a process. We're talking about kernel features like Linux namespaces, cgroups, capabilities, AppArmor, and SE Linux. Each one locks down a specific type of resource or functionality. The end result is that processes inside of a container appear to be running on their own separate computer, even though they're not. Let's take a brief look at these kernel features so that you can see what I mean. Control groups, or C groups for short, give you the ability to control how processes consume compute resources. You can use C groups to set lower and upper limits on the CPU and memory resources assigned to a process. Note that by default, containerized processes don't set bounds on compute resources. Where C groups can be used to partition compute resources, Linux namespaces are used to partition system resources. These are things like process IDs, inter-process communication resources, and network devices, to name a few. A process in a namespace only has access to the system resources assigned to that namespace. From that process's perspective, it's as if it has its own isolated instance of the resource. There are actually multiple different types of namespaces. Each one corresponds to a different type of system resource. For instance, the IPC namespace isolates inter-process communication capabilities. The network namespace isolates things like network devices and ports. The mount namespace isolates file system mount points. The PID namespace isolates process IDs. The user namespace isolates user IDs and group IDs. Finally, the UTS namespace makes the container appear to have its own host name. That's namespaces in a nutshell. Linux kernel capabilities provide fine-grained control over superuser permissions. This way, you can avoid using the root user when you only need a small subset of root capabilities. After all, running as root is a dangerous practice. These kernel features are used to lock down a program's abilities. Put another way, they are security features which restrict containerized processes. Now, you have a better understanding of how Linux containers isolate resources and restrict containerized programs from interacting with the outside world. Conceptually, Docker images are made up of a stack of layers. Each layer corresponds to a set of file system changes from previous layers. A Docker image is basically the union of all of these file system changes. For example, you might have an image whose base layer is a bare-bones version of Alpine Linux. The next layer might add Vim. The layer after that might add a text file containing sage advice like, wherever you go, there you are. Containers created from this image would run Alpine Linux and would then have Vim and a useless advice file on the file system. A critical property of image layers is the fact that they are read-only. The major advantage of this design is that an image can share some or all of its layers with other images. This is beneficial for three reasons. First, shared image layers can lead to significant space savings on the file system. The second benefit is that images are composable. You can create a new image by starting with another image and modifying it, i.e., adding some new layers to create a new image. The third benefit has to do with how images are pulled down from a remote image registry. You see, your Docker engine will only pull down the image layers which it does not already have. It won't download the shared image layers which already exist in your local cache. This optimization can save you a lot of time. Of course, the downside to shared image layers is that if you need to update an image, then you need to rebuild all of the other images which are based off of the original image. Thankfully, this doesn't happen very often. Because image layers are read-only, all changes to an image are additive in nature. For example, let's say that you want to build a new image from an existing base image. When you add a new file to the image, this will add a new layer. When you update an existing file on the image, Docker doesn't actually modify the file. Instead, it adds a new layer which contains the changes to the existing file. Similarly, deleting a file from a parent image doesn't actually remove the file from the file system. Instead, a new layer containing a whiteout file gets added to the image. The whiteout file indicates that the target file should be treated as having been deleted, even though it still exists in memory. Since every modification makes an image bigger, you need to be strategic about the changes that you make. Here's a quick summary. Images are composed of layers. Docker shares layers between images. Image layers are read-only, and layers are always additive. Finally, A layer only contains the difference between the original file and the new value. Containers are created from images. Here's how that works. A container shares the same read-only image layers as its parent image. That's how all of the files in an image end up in a container created from that image. Now, this brings up an interesting question. How do containerized applications write to disk? After all, image layers are read-only. Well, the topmost layer of every container is special. This so-called container layer is writable. Any time that a containerized application writes to a file, the data gets persisted onto the container layer. That's all fine and good when a program wants to create a new file. But how does a program in a container edit files that are stored on one of the read-only image layers? Well, the fine folk at Docker used the classic copy-on-write strategy to solve this problem. You see, whenever you try to edit a file stored on an image layer, Docker copies the file over to the container layer and then performs the edit on the copy. All subsequent read and write operations ignore the original file and go to the copy. Thus, the original has been overridden. Pretty cool, huh? There are 3 important benefits to this design. First, creating a container layer is a very fast operation. This is because all Docker has to do is create a thin, writable container layer. That takes virtually no time at all. Second, sharing image layers saves a lot of persistent memory compared to a strategy where image data is copied in order to create a new container. Lastly, since each container has its own container layer, each container can create or modify its files without affecting the other containers in any way. On the surface, containers are similar to another popular technology, virtual machines. They both have their advantages and disadvantages. By comparing containers to VMs, we can get a much better understanding of why containers have grown so popular. Let's start off by quickly going over how VMs work. Here's a computer. The bottom layer represents the hardware. On top of that runs the operating system. On top of the operating system run your applications. To run a VM, you need to run a hypervisor on the OS. This is the application that actually creates and runs virtual machines. It's important to note that every virtual machine runs its own guest operating system. The guest OS and the host OS are completely independent from each other. This means that you can do things like run Windows as your host OS while running Red Hat as the guest OS on a VM. That covers the types of virtual machines that you're most likely to encounter. At this point, we've gone over how containers work and how VMs work. Now we're ready to discuss the advantages and disadvantages between the two technologies. First off, VMs require way more memory and CPU than a container. This is because running a VM requires you to run a hypervisor and a guest OS, both of which are heavyweight applications. On the other hand, a container will usually only run a stripped-down Linux OS which shares the host OS's kernel. A VM might need a couple of gigabytes of memory, whereas a container might only need 4 or 5 megabytes. Second, VMs are slower to start up because you need to start the hypervisor and then boot up the VM's guest OS. On the other hand, containers are very fast to start up. Those are 2 points in favor of containers. However, there are some situations for which VMs are better suited. For instance, you can run any OS on a VM. On the other hand, a container can only run a variant of the host OS. This is because the container shares the kernel with the host OS, which is almost always Linux. For example, you can run Debian in a container, which itself runs on Red Hat. But you can't run an OS X container because it has a non-Linux kernel. Note that recently, Microsoft and Docker have worked together to create Windows containers. These containers run directly on the Windows Server kernel. Another way in which VMs outshine containers is that VMs provide better isolation. Here's why. A compromised process in a VM has to bypass the guest OS and the hypervisor before it can attempt to do malicious things to the host machine. On the other hand, A hacked container process only needs to take advantage of a Linux kernel vulnerability to gain control of the host. That's a consequence of the fact that a container shares the same kernel with the host OS. We're almost done with this extended introduction to Docker containers. Before we move on to actually creating and using containers, let's review the pros and cons of using Docker. Docker containers provide many benefits. For instance, they make deployments truly easy and repeatable. They improve resource utilization when compared to VMs. They provide isolation. They work well with just about every tech stack and programming language. Therefore, you can leverage your existing skill set. Docker images allow you to version an application with its environment. It all goes in source control now. Docker isn't well suited for every type of problem. First, a container cannot have an OS whose kernel is incompatible with the host OS. Second, VMs are more secure than containers. Third, images on Docker Hub might be compromised or malicious. It's up to you to verify that images are safe to use.
Believe it or not, you now have a pretty good idea of what Docker containers can do. They really are a transformational technology, so I hope that you're excited. In the rest of this course, I'm going to teach you how to use various Docker commands to create and run containers and images. Thanks for watching. I'll see you in the next video.